want to do today is I want to start with differentiating identities, and then I want to go from that and talk a little bit about the Gaussian distribution. I've deliberately tried not to review my notes about the Gaussian, so I can try to do this fresh, and we can try to talk about how you might approach attacking a problem you haven't seen before. Okay, so let's do a few more examples of differentiating identities. This is one of my most powerful techniques that I know. It's one of the things I turn to when I'm at a loss as to how to approach. What do you need to start a differentiating identity attack? What do you need? What's the first step? You need an identity. So the question is, what identity can you use? Almost always the identity is going to come from the fact that you have a probability distribution. So in addition to being non-negative, you have something that sums to 1. So somehow you want to use the idea that you have something that sums to 1. So for the binomial, we say x is binomial NP, and that means the probability that x takes on the value k is n choose k, p to the k, 1 minus p to the n minus k, 0, well, we'll do it this way. K is in 0 through n. And it's 0 otherwise. So it takes on integer values. So we know the sum k goes from 0 to n of n choose k, p to the k, 1 minus p to the n minus k equals 1. So we want to find the mean. So the expected value, or the mean, is going to be the sum k goes from 0 to n of k, n choose k, p to the k, 1 minus p to the n minus k. So somehow we want to use this expression to get to here. Your natural thought is, what should you do? What's your instinct to get from here to here? You've got to have some instincts by now. What would you try to do? Well, you're summing over k. You can't just multiply by k, right? What could we do to try to get from here to here? Take the derivative with respect to p. So we could try d by dp, or maybe p d by dp. These are the natural things to try. When the derivative hits the p to the k, this is really good. The problem is then it's going to hit the 1 minus p to the n minus k, and that's bad. And I'll leave it as an exercise, for you to go through and see if you can make this work. The problem is when these hit the 1, you get a 0. So then the question is, what's going to happen as everything goes through? Well, when I take the derivative with respect to p, I'm going to get a k, p to the k minus 1. That piece is going to be very close to what I want. When I take the derivative here, I'm going to get an n minus k, but the derivative of this is negative 1. That's actually helpful, because that'll give us a k minus n. So it looks like you'll have two pieces. The k's will combine and give you like a 2k. And then maybe you'll have a negative n, which will come over to the other side. So I strongly urge you to try to make this algebra work. There is a way, I believe, to make this work. So if you try what's most natural, eventually after some algebra work, you will use that d by dp of 1 minus p to the n minus k is k minus n, 1 minus p to the n minus k minus 1. And that's because when we do the chain rule, we're going to get an extra negative 1 coming from that, and that'll flip the order of this. But there's going to be a lot of algebra you'll need to do, because you're now going to have two different terms. They'll be to different powers. You need to get it looking like this. So there's a lot of algebra. It's doable. And it's worth doing so that you appreciate the other approaches more. Okay? I want to show you another way to do it. So the question is, are there any other identities we know that are similar to this? This is actually a special case of a more general identity. Does anybody know the more general identity?
Multinomial distribution?
That's one way. I don't want to go to the multinomial, but this is a special case of the multinomial, yes. But there is an identity involving just two things and a sum with binomial coefficients. We've seen an identity like this before. It's one of the key ingredients in calculus when you're trying to find the derivative of x to the n. So it's the binomial theorem. Problem with the blackboard line being there. X plus y to the n is the sum, k goes from 0 to n choose k, x to the k, y to the n minus k. Now for us, when we want to use the binomial theorem, all right, let's take x to be p and y to be 1 minus p. When we do this, x and y are related. And if I then take derivative with respect to p, I've got to use the product rule. If I just look at this expression, however, things are much nicer. I can differentiate this with respect to x first, then set x equal to p, then set y equal to 1 minus p. So if I do that, let's apply, do we want to do x d by dx, or do we want to do d by dx? Which do you think we're going to want to do to get the mean? X d by dx. Because when we do d by dx, we're going to lose one power of x. We'll have x to the k minus 1. We want x to the k. So when we apply this one, we end up getting x times n, x plus y to the n minus 1 equals the sum, k goes from 0 to n choose k, k, x to the k, y to the n minus k. Whoops. I didn't even think twice about interchanging the sum and the derivative. Is that okay? Are we allowed to interchange the sum and the derivative here? Or do we have to appeal to real analysis?
You're okay because it's finite?
It's finite. So because it's a finite sum, we don't have to worry about interchanging the sum and the derivative. So because it's a finite sum, this is okay. Now we set x equal to p, y equal to 1 minus p, and so x plus y equals 1. This just becomes 1 to the n minus 1. Okay, that's just 1. So we get on the right-hand side, we get n times p is equal to the sum, k goes from 0 to n of k, just switching the order, n choose k, p to the k, 1 minus p to the n minus k. So we've now shown that the expected value equals np. And this is a result we've shown earlier. So this, yes, did I make a mistake?
From that left side to np.
Because what does x plus y equal? X plus y equals 1. So 1 to the n minus 1 is just 1. So this equals exactly what we had before. So we proved the mean was np before by using linearity of expectation. And we recognized that a binomial was a sum of n Bernoulli random variables. Each one was 0, 1. It was 1 with probability p. We understood the sum by breaking it up into constituents. That's one of the other major themes of probability or mathematics, is you break up a complicated process into lots of simpler ones and you understand how they combine. So here, this is another way of doing it. We are studying the binomial distribution directly. And we've got two different ways to use differentiating identities to finish the analysis. Okay, any questions on the binomial distribution and how you would use differentiating identities? Okay, so I'll leave to you calculating the variance. So now that we've got the mean, you can probably figure out this is going to be the easier way to get the variance. The question is, do you want to do d by dx or x d by dx? They'll get you slightly different quantities. It's a real function of the algebra. The best way to figure out which one is better is to do both and then see which one was shorter and easier. The more of these you do, the more intuition you'll build up. All right, what I want to do now is I want to move to the negative binomial distribution. How many of you have ever heard of the negative binomial distribution? Excellent. Well, this is not excellent because you should have been reading the book, but how many of you can figure out what the negative binomial distribution probably generalizes? Probably the binomial distribution, based on the name, based on the fact that I'm writing it on the board immediately after doing the binomial distribution, the negative binomial distribution probably generalizes the binomial. Very similar to the geometric, very similar to a lot of the other things we've done, there are multiple ways of defining things like the negative binomial. There's a pretty much standard way, and I'll use that one, but you've got to be careful. Sometimes people use slightly different notations. This can be very annoying. Are you talking about what happens on the nth trial, or are you talking about how long it takes for a certain thing to happen? So for the negative binomial, so x is negative binomial RP, so have probability, let me make sure I do this right. So we have, okay, probability P of success. X is the number of successes before the rth failure. So we'll see if this is actually a generalization of the binomial or if it maybe is something else. The name seems to be implying the binomial. So essentially what I'm doing is I have a coin, I have probability P of success, and I want to keep flipping the coin until I have R failures. You know, R strikes and you're out. Okay? And I want to know how many successes do I expect to get before I get those R failures. Do you think eventually you will get R failures? What is the only way you will never get R failures?
If the probability of success is 0.
No, other way around.
Oh.
If the probability of success is 0, it's very easy to get R failures. Right? How long will it take to get R failures in that special case? R tries. So in the case when P equals R, this is not a very interesting distribution. As an aside, there were essentially situations like this. All right, munchkins need to be provided. Oh, good, worked out. All right. So in the old Soviet Union, there was a lot of anti-Semitism, and they had oral exams for PhDs, and they chose problems to make certain people fail. And the problems always would have simple solutions if you looked at them just the right way. And there's a famous story of one person who kept answering these problems and eventually was told by the examiner, how long do you want to keep going until we eventually stop you? There's some great articles on this. They're called killer problems when they try to write it diplomatically. But the exam was designed to keep asking questions until you got the failure from the person you wanted. Right? In almost every situation in life, if you do things enough times, you will get a certain number of failures. If you're good, it will take you a long time. And there was this one student who was just surviving everything they were throwing at him. And eventually, after hours, he finally just left in frustration. But in general, unless P equals 1, you will eventually get R failures. Now, it could take you a long time. The larger P is, the closer P is to 1, the longer time it should take you to have R failures. If you want an application of this, think of it as you have some system. And every, you have discrete moments in time, and every discrete moment in time, you have a chance for system failure. And you can survive so many failures. If you want to think of it as lightning hitting a grid, if too many lightning strikes hits your area, your network goes down. You can survive a certain number of hits. Think of it as naval warfare. Your ship can survive a certain number of hits. At some point, you have too much damage and you're dead. So we want to calculate what is the probability of getting exactly k successes before the rth failure. So we want k successes, and if you want, think of the k successes as heads, and we want r failures, think of them as tails, and then the probability of a success is p, the probability of a failure is 1 minus p. All right, so we have a string of s's and f's. What can you tell me? Do you know the location of any event? So we have exactly k successes, exactly r failures. The last one is a failure. Yes, because we're waiting until we get r failures. So we know we have to end with a failure. Did I talk in class about how good a team is if they've won 3 out of their last 4 games? Did we do that on the first day of class? So if I tell you a team has won 3 of their last 4, it sounds like the team is playing well. It sounds like they're playing 750 ball. Well, if they've won 3 out of the last 4, what happened 5 games ago? They lost. Otherwise, I would have said they've won 4 out of 5. So when I'm trying to figure out what's going on, there has to be a loss here. What must be true over here 4 games ago? They won. Why does that have to be a win? Otherwise, I'd say they won 3 in a row. I don't know what's going on in here. I know there's 2 wins and 1 loss. I'm sorry? Oh, sorry, I have lost sight. Thank you. That should be a win. Sorry. So in the last 3 games, the team has won 2 out of 3. In the last 5 games, the team has won 3 out of 5. This team is essentially playing around 500 ball. But you can make it sound a lot better. In this situation, when we say 3 of 4, we were actually waiting for a specific result. We were going all the way back until we got a win, and then looking for the next one to be a loss, and then we deliberately stopped. So if you want an example of where people do this, this is misleading with statistics. People deliberately present information in such a way as to influence how you view events. We know that we have to end with a failure. But inside here, we have K successes and R failures. How many slots do we have in here? I'm sorry? How many slots? So we have K plus R minus 1 slots. And so what we have to do is we have to choose exactly K of them to be successes. So the probability that X equals K, this is just going to be K plus R minus 1 choose K. We choose K of the K plus R minus 1 slots to be a success. The probability of a success is P. How many successes do we have? We have K. And how many failures do we have? To the R minus 1. But then we have a 1 minus P, right? Because the last one is a failure. Well, since we have this, we might as well simplify and just write it as P to the K, 1 minus P to the R. And K, always good to say where things live. 0, 1, 2, dot, dot, dot. OK. Does this look like a generalization of the binomial? So there is some things that look very similar to the binomial. We've got p's and 1 minus key p's to various powers. We have binomial coefficients. The difference now is the top and the bottom are both changing. So unfortunately, there is similarities with the binomial, but it's not quite a binomial. It actually looks more like something else. One of the big problems is the binomial only has finitely many possibilities. This has infinitely many. As long as your coin is not perfect, it could take you a very long time before you get that rth failure. Whenever you see something in math, you always want to try to ask, is there something similar to this that I've seen before that maybe this looks like? Or is there a special case we could look at? So if you had to choose a special case, there's the Smartass Choice for R, which I will not let you do. What's the Smartass Choice? No. 1 is not the Smartass Choice. R is the correct. 0 is the Smartass Choice. Right? If you think about it, I'm waiting until I have 0 failures. But if we wait until the first failure, so we could take R equals 1. And then we would get the probability that X equals K is going to be now K plus 1 minus 1, choose K, P to the K, 1 minus P to the 1 minus 1. Well, after doing some simplification, this binomial coefficient is just 1. We get P to the K, 1 minus P. Oh, I'm sorry. I'm sorry. It should just be to the 1. I'm sorry. I was looking at the wrong spot. Does this look familiar? Where have we seen this? It's kind of like the basketball problem. Which distribution was this? It's close to the... Anybody remember? Nope, I heard somebody saying it. The geometric. Now maybe we've changed the roles of p and 1 minus p. And this is why when I gave you the definition of the geometric the first time, the question was, do you want to be talking about successes or failures? Well, when I'm looking at it like this, if I'm measuring, am I measuring to the rth failure or am I measuring to the rth success? Depending on how you choose to define your parameters, things are going to look a little bit different. But fundamentally, this is a geometric random variable when r equals 1. We understand the geometric random variable. So now the question becomes, can we understand the negative binomial? So the first thing is it a probability distribution? So if we want to prove that this is a probability distribution, we have to show two things: non-negative and sums to 1. The non-negative is obvious because we've defined it as a product of non-negative things. Is it clear that it sums to 1? Technically, we need to sum this k going from 0 to infinity with the top and the bottom of the binomials moving. If you think about doing it algebraically, this should be a nightmare to prove that this sums to 1. But if you think about this as story time, okay, the story time proof is trivial. All right? Eventually, I get r failures. The probability that I get r failures is equal to the probability I get r failures on the 0th, 1st, 2nd, 3rd. Okay, so if I want to measure how many successes I have, I just have to look at all the different possibilities. So let me just write it clearly. So story proof. We want the sum to be 1. We have some number, say k, successes before hitting our failures. So we just have to add the probability k is 0, plus the probability k is 1, plus ... And basically, the number of successes has to either be 0, 1, 2, 3, 4, 5, 6, or 7. We know the probability of each of these events, so if we add them all up, it has to sum to 1. And this is essentially proof by story because we've basically split our possibilities into a disjoint union. You can't have multiple things happening. And we can calculate the probability of each one. Therefore, if we amalgamate them all together, that's going to have to sum to 1. So we deduce that the sum, k goes from 0 to infinity, of k plus r minus 1, choose k, p to the k, 1 minus p to the r equals 1. So when we want to try to calculate the mean, this should be the starting point. So if we want to calculate the mean, let me keep that up because we don't need the geometric anymore. So this has to be our starting point. All right, so we start with the following. The sum, k goes from 0 to infinity, of k plus r minus 1, choose k, p to the k, 1 minus p to the r equals 1. How do we get the mean? What should we apply? So what do we do to get the mean? Well, we can't multiply by k because k is an index of summation. So if I multiply both sides by k, I'd have to multiply outside the sum and then put it in. So I agree with you that we want to put a k in here. The problem is k is varying. And so whatever you do to one side of the equation, you have to do to the other. So if I multiply by k on the left, I've got to multiply by k on the right. Well, I've summed over k, so k is no longer available. So we want to somehow bring down a k. So we try p d by dp or d by dp. And unfortunately, when we do this, we're going to get a product rule again. You can do it. I go through the algebra in the book. It's not horrible. Is there a way to bypass the product rule? How could we bypass the product rule? Well, one of the things we saw when we, yes?
Multiply by RP.
Multiply by,
R times P outside the summation. Because you have P probability from R. Oh, wait, never mind.
no. We do want to multiply by 1 minus p to what power? I claim there's a really good choice of power of 1 minus p. What power should I use? It'll make this side so much nicer. I'm sorry? Not 1 over r, negative r. Because if I multiply by negative r, I now get the sum, k goes from 0 to infinity, of k plus r minus 1, choose k, p to the k equals 1 minus p to the negative r. And again, it's just a small amount of, it simplifies the algebra a little bit. You can do it by doing it directly here, but if you can learn these tricks, it'll make the algebra nicer. What's nice now is I no longer have a product rule. Normally something like this would be illegal. The reason we can do this is r is fixed. And we're using r is fixed. And because r is fixed, we can multiply it through to the other side. Now we apply p d by dp, and then we go through and do the rest of the algebra. So I'll try to quickly do that algebra now, because it allows us to review how you finish these problems. So now we apply p d by dp, and we'll get the sum, k goes from 0 to infinity, of k plus r minus 1, choose k, p to the k, is equal to negative r, 1 minus p to the minus r minus 1. But now I have to take the derivative of the inside, and the derivative of the inside gives me a negative 1. This is almost the mean. The reason it's not the mean is I need this factor of 1 minus p to the r. Well, good, I've got a 1 minus p to the negative over here. I bring this over to the other side, and now we get the sum, k goes from 0 to infinity, of k plus r minus 1, choose k, p to the k, 1 minus p to the r. The r's can reinforce, and it's r over 1 minus p. This is a lot faster than the algebra in the book. Okay, so whoever gets this chapter to work on, this would be something to write up and include. And again, it's the same idea, but depending on how you arrange the algebra, you can make your life so much easier. And it's worth it trying to think, what is the best way to attack this problem? What's the best way through this nightmare? The next question is, does this result make sense? We're saying the expected value of x is equal to r over 1 minus p, and here x is negative binomial rp. So whenever you see something like this, you want to try to vary the parameters in your mind and try to get a sense of what should happen. So as we increase r, do you think the mean should increase or decrease? What do you think? It should increase. We're counting how many successes do we have before we get the rth failure. I expect to have more successes if I'm waiting for the 15th failure than if I'm waiting for the 3rd failure. So you expect the answer to be increasing with r. How is it increasing? Is it linear? Is it quadratic? Is it square root? Is it logarithmic? I don't know. But it should be at the very least increasing with r. The next thing is, what should happen as p increases, as p gets closer to 1? Do you expect to have more successes or fewer successes for fixed r? So what do you think? As p gets closer to 1, do you expect to have more successes or fewer successes? More. As p gets closer and closer to 1, almost all the coins are now landing on a success, on a head. So in terms of how long it takes me to get r failures, I expect that to take more time the larger p is. And so my answer, as p gets closer to 1, the expected value should also rise. That fits this over here as well. This is not a proof that we've done the calculation correctly, but it's at least evidence that we're probably on the right track. Okay, So this is the negative binomial. Later in the semester, we'll talk a little bit about applications as to where you might use stuff like this. But I want to do right now just how you handle the calculations, how you can find the means, how you can find the variances. Okay, any questions about this? Okay, so now it's time to move to the Gaussian. So it's time to finally move to a continuous distribution today. So we've done a lot of discrete distributions. So Gaussian. So we say x is a normal variable with mean mu and variance sigma squared, means the density is the following. So it's 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. And so mu is the mean, sigma squared is the variance. Technically, we don't know this yet. We haven't proved that this has mean mu, and we haven't proved that it has variance sigma squared. We'll do that very shortly, or at least sketch how you would do it. But right now, all we've done is said, we're going to define this to be our quantity. Let me just make sure the camera's still looking. Yes, OK. All right. So we need to show, first of all, that the integral from minus infinity to infinity of fx of x dx equals 1. How many of you have seen this calculation in the Calc 3 class? The polar trick. Any student who's had me should be raising their hand right now. I know we've done this. So I will just quickly sketch what you do. So first, reduce to mu equals 0, sigma equals 1 by a change of variables. So you basically show that in the special case when mu equals 0 and sigma equals 1, you can calculate it by just changing variables. So you replace x minus mu with t, dx is still going to become dt. Then you replace t over sigma with u, and you just do this change of variables. So we just have to figure out what's going on in the special case when mu equals 0, sigma equals 1. In the book, I go through some arguments to try to show that this integral will actually converge. As long as the integral converges, we can renormalize it. It's clearly going to be non-negative because we're integrating a non-negative function. We just need to know that it's finite. So we want to study now the integral from minus infinity to infinity of e of 1 over square root of 2 pi e to the negative x squared over 2 dx. As an aside, this is twice the integral from 0 to infinity of e to the negative x squared over 2 dx. This is less than or equal to 2, the integral from 0 to 1 of 1 dx, plus the integral from 1 to infinity of e to the negative x over 2 dx. This is just a quick calculation to show the integral exists and is finite. The reason is I want to replace e to the negative x squared over 2 with something bigger that still integrates to something finite. Well, the largest value this is when x equals 0. When x equals 0, this is just 1. So when I go from 0 to 1, if I replace this with 1, I've just increased the integral. Now let's look and see what's happening from 1 to infinity. What I'm doing is I'm replacing x squared with x. Is that going to make this larger or smaller? So which would you rather have, e to the negative 100 or e to the negative 10? Which is going to be larger, e to the negative 100 or e to the negative 10? So this is making it much larger. Okay? So I'm replacing this with something larger. Why am I not doing this over here? Well, if x is less than 1, which is larger? E to the negative 1/4 or e to the negative 1/2? E to the negative 1/4 is actually larger. So I can't replace this with e to the negative x halves everywhere. This is only going to be larger than the integrand from 1 to infinity. So I break the piece up into two parts. And again, we don't need to do this. We're going to calculate the integral directly, but this is an incredibly important idea here. Trying to get a rough sense of what is the integral. Is it finite? If it's finite, we can renormalize it. It may be difficult to figure out what the correct renormalization is, but we'll know that one exists. And so by splitting this up, I've now broken it up to a function 1. I can integrate 1. And now I have an exponential. I know how to integrate the exponential. There's no closed form antiderivative for e to the negative x squared. All right, so now step 3 is the polar trick. I think there are only 2 things you can do in Calc 3. The 2 things you can do is you can switch orders of integration, and you can change variables. Now, this does not look like a Calc 3 problem because we only have one integral. So what we do is we write I squared is the integral from minus infinity to infinity e to the negative x squared over 2 dx, and then we'll use a different dummy variable, e to the negative y squared over 2 dy. So this is now the integral minus infinity to infinity, minus infinity to infinity, e to the negative x squared plus y squared over 2 dx dy. Whenever you see x squared plus y squared in Calc 3, you should have a Pavlovian response. What coordinates should you be thinking about? Polar, right? Probably the reason why this is directly underneath. Now, binomial going to negative binomial sadly did not work out, but today, yes, at least polar is a good label here. Whenever you see x squared plus y squared, this integral does not depend on theta. What this is telling us is we should change our integration, and this should be the integral theta goes from 0 to 2 pi, integral r goes from 0 to infinity, e to the negative r squared over 2, and then boy do we live life well. In polar coordinates, what does dx dy become? You need the polar transformation. What does dx dy become? Not d theta. R dr d theta. You should really view this as dr times r d theta. Think of x and y as being in meters. Dx dy is meters squared. It's an area. I want to look at how this area transforms. It can't transform just to dr d theta. That has the wrong dimensions. If you think about what's going on with a circle, here's my angle theta, here's my distance r, here's delta r, here's delta theta. And this gives me that small little area patch in the plane. And if I want to calculate what's the area of this patch, if this is r, the length of this arc is r delta theta. And then the length of this is, so this is approximately a rectangle, so its area is going to be approximately r delta theta times delta r. And this is where the r dr d theta comes from. Okay. What's really going on from your Calc 3 days is you need the determinant of the Jacobian change of variable, and that tells you how things are converted. All right, we have this. One of the integrals is easy to do. One of the integrals is a little bit harder. Which integral is the easy one? The theta. There's no theta dependence. We integrate theta from 0 to 2 pi. That's just 2 pi. Okay. Oh, actually, I've defined I to be with 1 over the square root of 2 pi, so I'll call this I tilde. So it's not the same I. Okay, so we've got a 2 pi here. Now we're left with the integral r goes from 0 to infinity of e to the negative r squared over 2 r dr. And this is where we are living life well. And the reason we're living life well is e to the negative x squared over 2 dx. We can't integrate that. We don't have a nice antiderivative. But if we want to do a u substitution, oh, this fits beautifully, right? R squared over 2, when we do a u substitution, if you let u equal r squared over 2, then du is just r d r. Even the 2's work out to our benefit. All right? So you end up getting 2 pi, the integral u goes from 0 to infinity of e to the minus u du. Oh, that's just the exponential probability distribution that integrates to 1. That's 2 pi. So we get I tilde squared is 2 pi. So this integral is the square root of 2 pi. It can't be negative. It's got to be the positive square root. And so now we know the normalization factor. So because it integrates to 2 pi, the normalization factor is 1 over 2 pi. So as I tilde equals 2 pi, normalization factor is just 1 over the square root of 2 pi. Right? And that's how you prove that this is a density and this is the correct normalization factor. All right. Whenever you have a density, what are the first few questions you should ask about the density? Mean and standard deviation, right? When you meet new friends on campus as a freshman, you might ask, where are you from? What are you interested in? How did you feel about the summer reading? Right? When you meet a distribution, you ask, so what's your mean? What's your variance? These are the natural questions. Okay? How can we calculate the means and the variances? Well, one way is we can go through and do brute force calculus. So the mean is not so bad. We want to integrate from minus infinity to infinity of x 1 over square root of 2 pi sigma squared. Well, I'll do it the painful way. E to the negative x minus mu squared over 2 sigma squared dx. All right. So the question is, how do we calculate the mean of this? Well, what we do is we do a change of variable. And if we do a change of variable, we've got an x minus mu. So if we change variable, let t equal x minus mu, so x is equal to t plus mu. And so when we do that and we come in over here, what we'll now get is the expected value of x is going to be the integral from minus infinity to infinity of t plus mu e to the negative t squared over 2 sigma squared 1 over square root of 2 pi sigma squared dt. Okay, so when we do that, that's going to be the expression we need to evaluate. We can split this up into two integrals, the t times this and the mu times this. Well, when the mu hits it, the mu integral is easy to do because it's mu times a density. Density integrates to 1. So the mu piece is going to just give us mu. What about the t e to the negative t squared piece? What does that give us? 0. We have an odd function. So the decay is sufficiently fast that we can handle it. T e to the negative t squared. When t is 5, that cancels with t equals minus 5. So we'll just get 0 plus mu. If this was a little bit fast, I urge you to either read the book or to go through and do the calculation slowly. All right, so this would be the mean. So this justifies our using the letter mu as one of the parameters for the normal distribution. Now we want to calculate the variance. And so what I'm going to do is I'm not going to calculate the variance in general. I'll just do the special case when mu equals 0. Because if I shift everything by 5, does it change the mean? If I shift all the values by 5, yes. Right? If I add $5,000 to your bank account, and I do that to everybody, the average amount of money in your bank accounts have changed. Have the relative differences between your bank accounts changed? No. So if I want to just calculate something like the variance, I don't really have to worry. I can always change the mean. So let's calculate the variance. So let's do the integral from minus infinity to infinity of x squared 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. All right, so this is the calculation we need to do. One way to do this is integration by parts. When you do this by integration by parts, u dv du v. I like to do integration by parts very slowly, very explicitly. If I do it like this, I'm not going to get confused as to what things are. What are the natural candidates to try for u? What could I try? I could try x squared. What else could I try for u? I could try x. What else could I try? For u, I could try x squared. I could try x. I could try the exponential. The problem is whatever I choose for dv, I have to be able to integrate. If I put an e to the negative x squared over here for my dv, I'm dead. I can't integrate it. If I put that over here, great. Well, when I differentiate it, damn, a 2x is going to come down. So if I put the exponential over here, when I differentiate and x comes down, not good. And when I go from here, then I would have an x squared here. Look, I get an x cubed. My degree is actually getting larger. So putting the exponential here is bad. Putting the exponential here is bad. So it looks like integration by parts is not going to work. The trick is to split up the x. And if you split up the x squared like this and have x and then e to the negative x squared over 2 x dx, now everything will work out. And the reason it will work out is now when I do the integration by parts, this is going to get me an exponential because I now have exactly what I need for the u substitution. And now when I go from u to du, the power of x is going to drop. And so when all the dust settles, if you attack it like this, using integration by parts, you will end up now having an integral without any x's, just with an exponential. And that's the probability distribution of the Gaussian. And now you can just finish the calculation. So you can do this using integration by parts. You can then calculate the general moments by just repeatedly using this. How else do you think we could calculate the moments of the Gaussian? What other method could we use? What other method could we use? Differentiating identity. This is the class on differentiating identity, right? There should be a way to use that to attack this problem. So let's go back, and we have the integral from minus infinity to infinity of 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx equals 1. All right, so if I'm going to do this, I'm going to want to somehow apply derivatives to this. So what are the possibilities to use? I've got to take the derivative with respect to sigma. But if I take the derivative with respect to sigma, I'm going to have a product here. What can I do so that I don't have to use the product rule? What can I do? Yeah, move it to the other side. We've seen this many times. Anything you see at least 2 or 3 times becomes a technique. It's no longer a trick. It's no longer an isolate. It's something you need to remember. If we move this to the other side, we now have the integral from minus infinity to infinity of e to the negative x squared over 2 sigma squared dx equals sigma times the square root of 2 pi. Now we can apply the derivative with respect to sigma. So if we apply the derivative with respect to sigma, what happens here? We're going to get a negative, so d by d sigma of negative x squared over 2 sigma squared. We get a negative x squared over 2. Now the derivative of sigma to the negative 2 becomes negative 2 sigma to the negative 3. The negatives cancel, the 2's cancel, and we'll get x squared over sigma cubed. Okay? So now it's all a question of what is the easiest way to do the algebra. If you look at this, we're getting a sigma cubed down here. What do we want down here? We want a sigma. Maybe we want to leave the square root of 2 pi over on the other side. And then at the end of the day, we'll need to just get a sigma over here. So I don't want to take d by d sigma of this. I want to multiply by how many sigmas? So how many sigmas do I want? 2. So if I multiply by 2 sigmas, now I get x squared over sigma. That sigma down here, when I put that sigma inside the square root, it's going to become a sigma squared. That's going to be the density function of the Gaussian. And so now, when we apply sigma squared d by d sigma to both sides, we now get the integral from minus infinity to infinity of 1 over square root of 2 pi sigma squared x squared e to the negative x squared over 2 sigma squared dx. All right, now we have to take the derivative of this with respect to sigma, 1, and then multiply by sigma squared. And here's the variance. Sigma squared. One line bypasses integration by parts. If you wanted to find the third moment of this, well, it's going to be an odd function, so the third moment will just be 0. If we want to find the fourth moment, we would play the game again. Once we get to this point, we would bring sigma over to the other side. So if we wanted to find a huge number of moments, instead of multiplying by sigma squared, what would we multiply by? So sigma squared was great because it gave us a 1 over sigma, which became a sigma squared inside the square root. But if I wanted to keep going, instead of multiplying by sigma squared, what might I multiply by? Because now if I take the derivative of this, I'm going to have to use the product rule. So instead of multiplying by sigma squared, what should I multiply by? I should multiply by sigma cubed. And so if I multiply by sigma cubed, then all of a sudden here I'd have a sigma to the minus 3 times sigma cubed, and that would fit perfectly. Okay, so this is a good place to stop. Okay.